guys, before we start our quiz, you need to make sure that you turned in 87 that I asked you to turn in yesterday. If you didn't turn that in Google Classroom, I need your hard copy to get full points. You'll also need to, it's no calculator, but you'll also need to put your phones and smartwatches up before I get you your quiz. So please get all that sorted. Wesley Jackson. Wesley School Business. Again, this is no calculator. Pretty short. About the same length as the practice quiz from yesterday. Of course, please check your work before you turn it in. Handouts you picked up, we will talk about once all the quizzes are in. And the quiz is number 88 for your binder. but it's still working. It's fine if you are, I just can't tell. Okay, then let's go ahead and move on here. So I need to introduce a little bit more to you today from section 3.1. Remember, this unit covers 1.9, which you have now seen what that is. 3.1, which is going to be exponential functions. So we need to know how to graph exponential functions, answer things about exponential functions. Indirectly, we need to know some exponent rules. And then there's a couple applications that we do for exponential functions. So we will go over 89 next. That was 2 of the handouts that you guys did or picked up on the way in. After that, we will go over most of 90. 90 is the front of one of those, the 3.1 worksheet 1, and 91 is the back of it. There is one question we'll skip on 90, and I will do 90 with you or for you, but 91 you'll be on your own. But you can see that they look similar. Okay, so first off, we need to know what it means to even be an exponential function in the first place. So an exponential function is when you have a variable up in the exponent. So something like 2 to the x or 3 to the x or 1/2 to the x, if the variable's up in the exponent, is considered an exponential function. All right, you really should have a good idea of the difference between what an exponential growth versus an exponential decay graph looks like. But the first time, I will go ahead and talk about, let's say you forget this in a few months. You could always just make a table and plug in a few points. Things like 2 to the 0 power is 1, because anything to the 0 power is 1. 2 to the first is 2. 2 squared is 4. And of course you could do more points, but that's enough to really figure out what the right side of the graph looks like. To do something like 2 to the negative 1, you'll have to remember an exponent rule where a negative exponent can move to the other side of a fraction and become a positive exponent. So 2 to the negative 1 is the same thing as 1/2. And same thing, you can plot more and more points. The more points you do, the more accurate it would be, but that's already pretty accurate. That's what 2 to the x would look like. Whereas 3 to the x is going to have a lot of similarities, because 3 to the 0 is still 1. Anything to the 0 power is 1. 3 to the first would be 3. 3 squared would be 9. How about 3 to the negative 1? What would that be?
1/3.
Good. 1/3. An exponent of negative 1 in the numerator is the same thing as an exponent of positive 1 in the denominator. And you could do more points to the left as well. But the main thing I need you to see out of this is that these two graphs are almost the same thing. One of them rises a little bit quicker to the right, and one of them hugs the x-axis a little bit quicker to the left. But for the most part, exponential growth problems all look the same. 2 to the x looks like this, 3 to the x looks like this, 5 to the x would look like this, e to the x would look like this, 10 to the x would look like this. All that changes is how quickly this goes up and how quickly it hugs the x-axis here. So anytime it's exponential growth, we know the general shape of the graph quickly. And hopefully you don't have to do a table, but you can always do that as a backup. Whereas in exponential decay, if we did the same thing here, if I plugged in 0, I would get 1. Anything to the 0 power is 1. I'm going to say that probably 300 times in the next couple weeks. 1/2 to the first would be 1/2. 1/2 to to the negative 1. This is another exponent rule that you may or may not remember. But if you have a bunch of stuff raised to the negative 1, you can change it to be raised to the positive 1 if you take the reciprocal. So 1/2 to the negative 1 is like 2. 1/2 to the negative 2 would be 4. So really, this just ends up being, this is just like 2 to the x, except it's been flipped over the y-axis. In fact, on the next page there's a graph, and I'll point that out again. So one of the things we expect you to do with exponential graph questions, you'll see when we get to worksheet 1, is we need to know a general idea of what the graph looks like. If it's 2 to the x, 3 to the x, 5 to the x, it's going to basically look like this. If it's 1/2 to the x, 1/3 to the x, 1/5 to the x, it's basically going to look like that. We should have a good idea of what the shape of the graph is going to be. Now, we are still going to do transformations to those. So the transformations are still consistent with what we've used earlier this year and what you used last year. If you add to the parent function, it goes up that much. You subtract from the parent function, it's going to go down that much. 6 and 7 are the two that you guys like to mix up sometimes. Adding to x makes it go left that much. Subtracting from x makes you go right that much. Same way we graphed trig functions last semester. It's consistent with that. Multiplying the parent function by negative is going to flip or reflect your graph over the x-axis. And one that you've heard before, but you just don't get to practice as much, if you replace x with a negative x, that's not the same thing as multiplying the parent function by negative. If you just multiply the x by a negative, that's how you flip it over the y-axis. And this one I can give you a good example of, because 2 to the x looks like this. If I wanted to flip it over the y-axis, I could make it be 2 to the negative x, as long as you know how to change this with exponent rules. 2 to the negative x is the same thing as 1/2 to the positive x. You can change a negative exponent to be a positive exponent by taking the reciprocal. So, two of the graphs that we did on the front page, you can now see why those are y-axis reflections. The x just got replaced with a negative x, and then we did exponent rules to make it look a little bit different, but otherwise the graphs look the same. So, there's not much that you need to fill out on this page, but it does remind you that we will be asking questions like domain, range, y-intercept, increasing, decreasing, all of that kind of stuff. So I feel like that would benefit some of you, so I go ahead and print it out for you. But skip down to this. So I've already said a few of these today, but if we just assume you remember all the exponent properties that you're supposed to know, then that's going to mess you up some the next couple weeks. So I'm going to explain each of these. Some of these are duplicates, but what you need to do is follow along and probably put stars by the ones that you didn't know or you hesitated on. So this one I've already said a few times today. Anything to the 0 power is 1. These three are basically saying the same thing. This is saying an exponent of -1 in the numerator is the same thing as a positive exponent of 2 in the denominator. A negative exponent of 3 in the denominator can move to the other side of the fraction and become a positive 3. A -4 exponent in the numerator can switch to the other side of a fraction and become a positive 4. So all three of these are basically the same thing. Most of the time in mathematics, we don't leave answers with negative exponents. Usually you need to rewrite it so it has a positive exponent. This is probably the one you have the most familiarity to, but it just looks kind of funny. This one deals with x times x. When you multiply things with the same base, you add the exponents. That's why x times x is x squared. If you divide things with the same base, you subtract the exponents. Bless you. So I think if you saw something like this and you had to simplify, you would probably think of it as these two x's cancel out those two x's and leave you an x. But you can also think of it as subtracting the exponents to get to that. If you raise a power to a power, those powers gets multiplied. So something like x cubed squared would mean x cubed times itself twice, which would be x to the 6th. Notice how the exponents get multiplied. If you raise parentheses to a power, then everything in those parentheses get raised to that power. X got raised to the m, y got raised to the m. And then this one is the same idea, just with numbers. If you raise 2x to the 3rd, then the 2 gets raised to the 3rd and the x gets raised to the 3rd. Now again, some of these we're going to use a lot, some of them we'll just use a little bit, but this will be our couple weeks till spring break, and then even after we come back from spring break, a couple weeks. So any of those that don't sound intuitive to you, just put a X or put a star by them and make sure you look back at them later. Okay, and then for our application questions, there's two types of applications we ask you to look at here. This first one, I wish we had time to have done this before the ACT, because my 8A classes were telling me they saw this on the ACT. So you still could have known it from Algebra 2, but. And the first is the compound interest formulas. So if you compound continuously, there's a formula called PERT. This is a really important formula. In fact, even in my calculus classes yesterday, they were doing some calculus where they had to use that PERT formula multiple times per question. And if instead of being compounded continuously, it's compounded a certain number of times per year, we have this formula. Sometimes students call this the print formula because it almost kind of looks like the word print. That's not a real thing. That's not its real name. So we'll practice some questions with those on worksheet 1, but what you need to notice is both of these have a P in them. P stands for principal, or the starting amount. Now these formulas work both ways. These could be like if you got a loan, how much you're going to have to pay back, or it can be like an investment. You're putting money in an investment and how much it's going to be worth at the end. So, but the starting amount, P, stands for principal. Both of these formulas have a T, which represents time in years. So if it's 4 years, you'd put 4 in place of T. Both of these formulas have an R, which stands for the rate, and the rate must be put in as a decimal. So if it's 50%, you would need to put 0.5 for R. If you put 50 in for R, you're going to be doing 5,000%. If you want 5%, it would be 0.05. Has to be entered as a decimal for it to work. So both formulas have those three things: principal, time, and rate. What is different about these two is the PERT formula has an E in there. E is not a variable. E is a number. E is about 2.718. It's like pi, in that the number pi, and that it is an irrational number, meaning that its decimal doesn't have a pattern and continues forever. It just naturally appears. In fact, on the bottom of this page, I'll tell you where E comes from. And then the other formula has N in it twice, where N represents the number of times compounded per year. So if it's not compounded continuously, you have to be told how many times it's compounded per year. So if it said annual, that would mean once. Quarterly, it would be 4 times a year. Monthly would mean 12 times a year. Daily would be 365. Those are some of the more common ones. Could be semi-annually, which would mean twice a year, but those are the big ones. However many times it's compounded per year, you would plug in place of n. So for the most part on these two formulas, we expect you to memorize them. You need to know what each variable stands for, but then you just have to plug the numbers in where they go. So again, we'll actually do it with some numbers on worksheet 1 in just a minute. All right, the other application that we're going to do, I typed up an example that you might want to read through later, but it's about half-life, and you don't need to know any chemistry to be able to do half-life, except you do need to know, I guess it doesn't say here, half-life just means the amount of time it takes for half of something to decay. So if there's like something that is 100 grams, the time it takes for it to deteriorate to 50 grams is called as half-life. So again, there's an example here, but I don't know that you really need to read through that. You'll see when we do an example in worksheet 1. Okay, and then finally, just to give you an idea of where the number E comes from, so you can put, we won't quiz you on this, you don't have to memorize this for us, but we do like you to know that E is not just some random assortment of decimals. E comes from taking 1 plus 1 over x to the x power as x goes to infinity. Just like the number pi isn't just completely made up. You guys know where the number pi comes from? 22%. Huh? 22%. Now that's what it's approximately equal to.
It's the circumference divided by diameter.
Very good. If you take the circumference of any circle and divide it by its diameter, no matter how big or small your circle is, that's where the number pi just naturally gets created. Same thing with E. E, this pattern just happens to occur naturally in a lot of different things. So that's why it becomes important in math. Okay, let's actually, so that's just a quick little reminder of some stuff. Let's look at worksheet 1. So this would be the front of this page. Again, this is the one I'm still going to walk you through, but I will ask you to do the back worksheet 2 that you can see is very similar. So you need to make sure you're picking up the stuff that you need. Again, some of this should be familiar to you from Algebra 2. This should not all be new to you. If it is all new to you, then you probably need to review it a little bit more than everybody else for homework. All right, but question 1 gives us a function, and we're doing this without a calculator. And it asks a ton of stuff about it. Domain, range, asymptotes, increasing, decreasing, some points, etc., etc. So my suggestion to you, and what I'd like you to do for your notes, and you're welcome to steal this on worksheet 2, unless you have something that you'd prefer to do. But when I look at this mess of a function, I can look through there and see that the parent function would be 3 to the x. And I know what 3 to the x looks like. I'm just going to draw a real rough sketch. If I can get a sketch of this function, I can answer most of these things reasonably easy. So the first transformation is going to shift it left 1, because if I plug the number into x, the first thing I would do is add 1, and that transformation shifts it left 1. So if I know what this looks like, I can try to shift it left 1, and I have an estimate of what 3 to the x plus 1 looks like. What does the negative in front of the 3 do?
Flips it down, right? Over the x.
Right, flips it over the x-axis. So let's try to do that. And then finally, the one I really want, this exact thing with the -1. And what's the -1 on the outside here do? One more time. Down 1. So take this, try to make it look like it's gone down 1. And now we have a pretty decent sketch that's going to help me answer most of these questions about number 1. Also, I think it's good to have those other steps in there on your paper. So don't just try to do it on one graph. And you'll see why when I start answering this. Okay, so domain. I'm going to look at this graph and then slowly apply it to this graph. 3 to the x goes forever to the left, and it goes slowly to the right, but this does keep drifting to the right as you go that direction. So this guy goes forever left, forever right. Shifting it left 1 doesn't change that. Flipping it over the x-axis doesn't change that. And shifting it down 1 doesn't change that. So this guy's domain is -infinity to +infinity. He goes forever left and forever right. If you try to answer the range based on this, you might miss it. And that's why I think it helps to have these here. What is the range of this graph?
0 to infinity.
Okay, 0 to infinity. You shift it left 1, still 0 to infinity. You flip it over the x-axis. Now it's -infinity to 0. And then you shift it down 1. Now it's -infinity to -1. That's where I think having these previous steps gives you an easy question, lets you think about how it changes, lets you think about how it changes, lets you think how it changes, and then it's a lot easier to answer. Okay, these do have horizontal asymptotes. This one had one at y = 0. You shift it left 1, it's still at y = 0. You flip it over the x-axis, it's still at y = 0. But then we shifted it down 1, so now it's at y = -1. These kind of look like they have a vertical asymptote because this is kind of going up quickly. But again, it does keep going to the right. So a vertical asymptote would have to go straight up at some point. So these do not have any vertical asymptotes. When we get to section 3.2 and we're talking about graphing logarithm graphs, these two would be switched. A logarithm is just an inverse of an exponential. So exponential has horizontal, not vertical. Logarithmic will have vertical, not horizontal. Yes?
This does not exist. We use that here.
Yeah, you could say does not exist. That's fine. Okay, increasing, decreasing, just as a way to describe the direction of the graph. So just like you read a book left to right, you should read a graph left to right. It's increasing here, still increasing. Now it's decreasing. That's decreasing. Reading left to right, the graph is going down, so he is decreasing. My 8A classes told me that they did not talk about concave upward or concave downward in Algebra 2, which is a little bit different, but it's an easy one to pick up. And those of you doing calculus next year, we talk a lot about concavity. The concavity of the graph tells, depending on what the graph represents, can tell you a lot of real-world stuff. So concave upward, if you've not heard this before, you probably should jot this down. Concave upward is when the graph opens up like a cup, whereas concave downward opens down like a frown. Up, concave up like a cup, concave down, down like a frown. So here is concave up because it's opening upwards, still concave up, but then as soon as we flip it over the x-axis, now it's concave down, concave down. Concave downward. All right. G wants to know the order pair when x is 1. So here's about where x is 1. You should not be trying to answer this by guessing. This is a sketch that was pretty good to help me feel good about most of this here, but it's not good enough for me to know the y value when x is 1. So what's a different way for me to know this point besides trying to look at this rough sketch? Very good. So algebraically, solve for y when x is 1. That would be negative 3 squared minus 1, which is negative 10. Now, if that had got me an answer of positive 10, I would be concerned, because it definitely doesn't go through 110 on my sketch. 1 negative 10 is possible. My sketch doesn't really make it look like it's going down that quickly, but it is going down very fast. So, okay, the next question, you should do the exact same thing. A y-intercept is when x is 0. So you don't need to try to get it from the graph. Just do it algebraically. The algebra is actually meant to make it easier for you. Plug in 0 for x, solve for y, and make sure that it seems reasonable to your graph. My y-intercept looks to be negative, so I'm not concerned about negative 4. If my y-intercept looked to be negative and this was positive 4, I would be concerned. Something would be wrong. Okay, the next question we have already talked about because we did this. First transformation we did was go left 1. The next transformation we did was reflect over x-axis. And then the last transformation we did was to shift it down 1. So by doing those graphs at the top, you've already thought about the order of the transformations. They just want you to verbalize it in words. All right, question J is one of 2 things you don't have to memorize for our quiz. So you can put an X through it so that you don't study it. But I do still expect you to fill it out on your homework because I'm going to tell you what the answer is. Sometimes these are referred to as transcendental functions, which doesn't mean anything to you right now. But if you look at a bunch of different calculus books, all calculus books on the front will either say early transcendental functions or late transcendental functions. So some calculus books deal with the calculus of these type of functions early, and some calculus books deal with the calculus of these type of functions later. So there's just 2 different philosophies on that, but sometimes these are referred to as transcendental. K wants us to make an accurate sketch, so not just a rough sketch, but an accurate sketch of this function. Well, we've already done the hard part. We've got a point, 1 negative 10, put it on your graph. We've got a point, 0 negative 4, add that to your graph. We've got a horizontal asymptote at y equals negative 1. And my sketch can still help me here because the sketch gives me a general shape of the graph. And so I just need to sketch in that general shape that I had already figured out. And you can be consistent that this still has the domain we said, it still has the range we said, it's still decreasing like we said, it's still concave down like we said. But just those couple points and the horizontal asymptote and the general shape of the graph gives you a very accurate graph pretty quickly. I believe on our quiz and or our test, we might specifically ask you to do like 3 or 5 points just to make it a little more accurate and to maybe help you catch some of your mistakes while you're taking the test. But L wants to know the 2 things that have to be true to be 1-to-1. So we've talked about that just last class. That would be vertical line test and horizontal line test. This passes both of those, so we would call this a one-to-one function.
How would you determine the rest of the points?
Here,
Yes, sir.
just the same way we did these. I mean, you could plug in 2 for x and solve for y.
Gotcha.
The number, like, I can tell by my graph that 2 is going to be something really big negative, so it may not be the easiest arithmetic, but 2, negative 28, so, but you could do some stuff like that. Okay, n is the other one you can put an x by, in the sense that we will not ask you on the quiz, so you don't have to memorize it. You still have to fill it in for your homework grade. Euler's number, that's the number E. E is base. Euler was a very, very famous mathematician. His name sounds like it starts with an O, but it's actually an E. So that is the one where 2.718 blah, blah, blah comes from 1 plus 1 over x to the x power as x goes to infinity. Again, you don't have to memorize that. We just want you to have at least seen it. A is one that I will show you next class. So when I ask you to do worksheet 2 in a couple minutes, that is just like worksheet 1. Worksheet 2 has a question like this. You can skip that one until Tuesday. And then finally, our 2 application questions, compound interest and half-life. So for the compound interest, you will have to know that PERT is the one if it's compounded continuously, and if it's compounded some other time, it's this one that some students call the print formula. Our quiz and I think our test is no calculator, so all we would be able to do is ask you to plug the numbers in. So starting amount goes in place of P. Regardless of which formula you're using. The rate goes in place of R as a decimal for both formulas. The time in years still goes in place of T. And that's all you need for the PERT formula. If it's the other formula, you still need to plug in for N. So N is going to be the number of times it's compounded in a year. So if it's compounded daily, N would be 365. Again, both of these formulas work whether you're talking about investments or loans, depending on which way you're going. Also, 6.5% is pretty tough to come by. You can get about 5, maybe 5.5% right now, just because interest rates are up. But in theory, if you have $2,000 that you could just put away for a while, you find some way to get 6.5%. If you can leave that alone for 30 years, this would end up turning into about $14,057 if it's compounded continuously. And if it was compounded daily, you would just put that in your calculator the way it looks. And to be honest, compounding daily is pretty close to being compounded continuously, so they're going to be pretty close numbers. This one would be $14,054.93. Does anyone remember seeing that on the ACT the other day? Something like that? Okay, do you know on the ACT, did it like expect you to type in the calculator, or did it leave it like this?
I think it wanted it like,
Typed in?
yeah.
Okay.
Well, yeah, find the result.
Okay. Again, what I have highlighted is what I think we'll be asking you to do on the quiz, because we won't give you a calculator, so you just have to set it up. So again, that's if you invested $2,000, but it goes the other way also. If you wanted to borrow $2,000 and they only charge you 6.5%, usually they're going to charge you more than that, and it took you 30 years to pay it back, that $2,000 that you could get today, at the end of 30 years, you end up paying them over $14,000 for that. And 30 years sounds like a long time, but 30 years is standard for a house. So someday you guys borrow a lot of money to buy a house. If you just make the payments and you don't try to pay it off early, you pay a lot of interest over 30 years. You end up paying for the house multiple times over, unfortunately. It's much cheaper if you just have cash to pay for it up front, which of course is also impossible, but you do want to pay it off as fast as you can reasonably. All right, and then the last type is half-life type problems. So again, you don't need to really know any chemistry behind this other than to know what half-life means. Half-life is how much time has to pass before half of something decays. So we have some made-up radioactive isotope, and this formula tells us how many grams it has based on the year T. So if you want to know the initial mass, initial is at the start, you should plug in 0 for T and solve and see how big that isotope is. What is 0 divided by 2007? Okay. What is 1/2 to the 0 power? 1, because anything to the 0 power is 1. So you're left with 40 times 1. 40 grams. Now, the answer was sitting right there, but again, you don't need to memorize where the answer is coming from. Just plug in 0 for T and solve. The second half of this question, how many years would have to pass before it reaches half of its initial mass? So if this tells us how much mass there is, and we know he starts off with 40 grams, we can measure his half-life by trying to figure out how many years have to pass before it becomes 20 grams. So same thing, you shouldn't try to memorize where the answer is, just set it equal to half, 20, and then solve. Divide both sides by 40. The left side becomes 1/2 to the first. The right side is 1/2 to the T over 2007. So the only way these two equations are going to be equal is if 1 is equal to T over 2007, which means T would need to be 2007. So the answer is sitting in the equation. But again, you don't need to memorize it that way. Just set it equal to half and solve for the amount of time. Now, one kind of interesting thing before I give you some time to work on worksheet 2 is there's lots of stuff that have half-life, specifically medicine. Anytime you guys have ever taken medicine in your lifetime, all medicine has a half-life. So it's got to take so much time for half of it to go away. Which means whatever you took as medicine as a kid, after so many years, it was half as much. After that many years, it was half of that. After that many years again, it's half of that. So when is it completely gone?
Take a long time. Never.
It's never. It's half of half of half of half of half of half. But every medicine that you've ever taken, there's still trace amounts of it in your body forever. So,
But it's just super, super, super small amount.
yeah, it's very close to 0, but
But it's still there.
it's still there. Yeah,
Never ever going away.
right.
Wow, that's great.
So,
caffeine too?
I don't know if caffeine has half-life.
Okay.
I don't know about that. Yeah.
What happens if you do like the half-life of just one atom?
I don't know. I don't know if enough chemistry to do that. I know I took physics classes in college instead of chemistry classes, so I know very, very little chemistry. Okay, so what I would advise you guys to do is look at how I think you should approach question 1 with the graph. Look at how we did the interest formulas and the half-life formula. And then you need to try all of this on the back worksheet 2. Part O is the one that you can worry about next class, because I didn't show you how to do that on the front either. But the rest is just one practice of each type. So, you guys still have about 32 minutes. So that's probably about right. So, go ahead and try to finish up that back page. Check your answers on the website. And if there's something that you're struggling with, go ahead and let me know. Next class, I'll show you how to do the one that we skipped. But I feel like you had enough content after that we should probably wait on that part. So. And of course, make sure you're doing that without a calculator so that you're not tricking yourself to think that you understand it better than you do.